Welcome to this lecture series in group theory. In this lecture, we'll be discussing the second isomorphism theorem, and let us recall a few things that we'll be using in this lecture. So we saw that if a and b are two integers, not both of them 0, then this particular subgroup, which is a sum of two subgroups. So in an abelian group, the sum of any two subgroups is again a subgroup, and we saw that this particular subgroup is actually equal to that. And this was a consequence of Euclid's theorem. And we also saw that the intersection of these two subgroups is this particular subgroup. And therefore, the GCD and LCM have group theoretic interpretations. We'll also use the first isomorphism theorem. All right, here are the problems. And let us get started with the material of this lecture. So we start with the lemma. Suppose n is a normal subgroup of a group G and H is any subgroup. We define Hn, this is just a notation for that. You just pick one element from H and another from N and multiply the meaning, operate the binary operation here and put all of them in a set, that is Hn. So we first claim that this guy is actually a subgroup, and the second is that N is a normal subgroup of that guy. This will be trivial, but let's see a proof of that. Okay, so here is a proof of 1. Let H1 and so we want to show subgroups, so we pick two arbitrary elements. Let me just skip one step and pick two arbitrary elements in Hn. So implicitly, this is these two are members of capital H and these two are members of capital N. So I'm not writing that. What we want to show is that it suffices to show that this guy is also in Hn. So this is what we want to do. This is a one-step way to decide subgroups. If you have a subset of a group G and you want to show that it is a subgroup, all you need to do is show that pick two arbitrary elements in capital H and show that this guy is also in H. That's it. So that's what we'll do. So, but what is this? This is equal to N1 inverse H1 inverse H2 N2, which is equal to H1 inverse H1, N1 inverse H1 inverse H2 N2. So what did we do? We just put an identity here. Identity doesn't change anything. And let me put brackets. So we put a bracket here. And since N is a normal subgroup, and this is a member of N, and this is a conjugate, this kind of thing is called a conjugate. So by normality of N, this is also in N, and we will write that thing as, I don't know, let's say N1 prime. So N1 prime is also a member of N. All right. And by a similar kind of trick, we have this is equal to so here again we just inserted an identity. And let me put a bracket. So with this bracket, again, since N1 prime is a member of N and by normality of N, this is also in N. And therefore this is equal to H1 inverse H2, N1 double prime, N2. But this is equal to Hn, where H is that guy and N is that guy. And since H is a subgroup, this is in capital H, and since N is a subgroup, this is in capital N. So this whole thing ultimately is a member of Hn. And this is what we wanted to show. So this proves that Hn is a subgroup. The normality of N in Hn is clear since N is contained in Hn. And N is a normal subgroup of G. So all I'm saying is that if you have a normal subgroup of a group G, and K is a subgroup such that N is contained in G, then it follows that N is normal in K. This is a trivial fact. So this is all that you need to do this guy. This was to... Okay, so let's go to the proof of, or rather the statement of the second isomorphism theorem. So the setting is the same. We have a normal subgroup of a group G and H is another subgroup. We just saw that Hn is a subgroup and N is normal in that. So this quotient is a legitimate group. It is legitimate to consider this quotient. And also there was an exercise earlier that this guy is normal in that. So, I mean, one way to see it is the following. Just consider this map. H included in G, mapping to G mod n. What is this map? This map just takes little h to h. This is a group homomorphism because h is a subgroup. And this is just the natural projection map pi. So you see the kernel of this map pi will be h intersection n. And therefore h intersection n appears as the kernel of a group homomorphism. And hence it is normal in H. So that is one way. Otherwise, you can just do the computational way, and that's also completely fine. Okay, so we want to show that these two groups are isomorphic. And as usual, we'll use the first isomorphism theorem. We will not throw a map from the quotients to themselves. We will start with a sort of a freer object, so to say. So consider, we have this group H. It is a subgroup of Hn, so we can take the inclusion map. So this map just takes H to H. This is a group homomorphism. Then we quotient this out by n. And this is the natural projection map. Let us call it pi. And we hence have a composite, which is again a homomorphism. Composition of two homomorphisms is a homomorphism. Let's find out its kernel. So what is the kernel of this guy? Let us call this phi. So phi of G, or let's not call it G, phi of H is by definition Hn. That's what it is. So this is the identity of the group. So okay, so kernel phi is those elements in the group H such that Hn is the identity of Hn mod n, but that is n. So it is those elements in H such that H belongs to n, which is precisely H intersection n. So the kernel of phi is H intersection n, and hence we have 5 factors through this quotient. This is where we use the first isomorphism theorem. This is phi bar, and this is an injective map because we have factored out by the kernel of phi. All right. Lastly, we'll verify that this is surjective. That's very easy because if we pick an arbitrary element of this guy, what does an arbitrary element of that look like? An arbitrary element of that looks like Hn, n, but that is equal to Hn because little n is already a member of capital N. This is equal to that. And clearly this is in the image of phi, just phi h is equal to that. So this is phi is a surjective map. Let me put a double arrow. Surjectivity is denoted by double arrows. So phi is a surjective map, and if you factor out a surjective map, it remains a surjective map. So this is also surjective. You can check that formally also, but that's like a trivial thing. So what we have finally is that phi bar is an injective and surjective group homomorphism, and hence a group isomorphism, which proves that the two groups that we wanted to show are isomorphic are indeed isomorphic. And that's it. So it's a very nice application of the first isomorphism theorem. And now let us look at a number theoretic application of it. So suppose we have two integers, a and b. Then this group, which is again a quotient of two groups, it's in the, let me put it in the previous setting. So if you want to put it in the previous setting, just take h equals az and n equals bz, g is z, and that's it. So let me check the h, and h is, no, I don't want, yeah, it is fine. H is az, that's fine. So if you take h as az and n as bz, you get this isomorphism. And this will be a consequence of the above thing. Why is that? As we saw, az plus bz is nothing but GCD a comma b. So we are assuming not both of a and b are 0. Or let's say a and b are both non-zero, because otherwise it's a trivial thing. So let's say a and b are both non-zero for simplicity. So this thing is this quotient. And the other thing, az quotiented by az intersection bz is az quotiented by LCM a comma bz. So these are both finite groups. I'll let you check. So what is the cardinality of this guy? Cardinality of az plus bz. This implies that the cardinality of az plus bz quotiented by bz is nothing but GCD a comma b. Sorry, this is b divided by GCD a comma b. And the cardinality of az quotiented by this intersection is LCM A comma B divided by A. So maybe this is not very clear, but all I'm using is this fact that suppose M divides N, then cardinality of MZ modulo NZ is N by M. So this is all, and this I leave you to check this. This is a very simple thing. You can also use this isomorphism from Z to MZ. You can use the fact that this map, which takes X to MX, this is an isomorphism, and you can use this also, but it's clear directly. So this is all that I'm using to get here, because this guy is nothing but that guy, and the cardinality of that is this. Cardinality of that is that. And if we equate these two things, we get GCD into LCM is A times B. So we saw this in a different way. We saw this previously in a slightly different way, but here we see it as an application of second isomorphism theorem. So it's a group theoretic consequence. And I really like this application. So yeah, I want to end this lecture on this. As usual, like, comment, share, subscribe. I also have Patreon. The link is in the description below. Thank you for listening, and I'll see you next time.